Today, we are presenting our research about an enhanced energy saving algorithm for narrowband IoT indoor localization based on convex optimization. I'm Renato Armaalio III from Southern Luzon State University. On behalf of my co-author, Engineer Soren P. Mabunga, I will present this research. For the introduction, the Internet of Things has rapidly evolved. It's becoming crucial component in modern connectivity by linking vast network of devices. One of the most transformative aspects is its capacity for real-time data monitoring and processing. The IoT's ability has significant implication for responsive and proactive decision making, specifically to areas where immediate response or feedback is needed. IoT is really revolutionizing various domains such as healthcare, agriculture, manufacturing, and many more industries. One of the key features of IoT it is the energy harvesting technology that powers each devices by collecting ambient energy that reduces dependency to traditional power sources that leads to the term of green computing. So what are the challenges in IoT networks? We have rapid IoT adoption and an increase in devices puts pressure on the system or the existing network architectures, leading to performance degradation. IoT networks also face several key issues. Number one, the need for efficient energy consumption. Another one, management of co-channel interferences and the data rate fairness amidst the high device density. So NMA, which is a non-orthogonal multiple access signals share the same frequency resources. It improves its spectrum utilization and it enables massive connectivity. So based on literature, they have previous studies explored the application of NMA and the energy harvesting in IoT. However, there's still a challenge that persists in balancing each of the components such as energy consumption, data rate fairness, and spectral efficiency. So what are we trying to solve? We're trying to solve a significant advancements that has been also the limitations of IoT. So limitations remain in current approaches regarding this criteria. Our study will address this gap by developing an integrated algorithm to optimize energy and spectral efficiency in high density device environments, specifically tailor fit for indoor localization where accurate data rate and energy management are critical. So for our methodology in summary utilizes a convex optimization approach to reframe a non-convex interference problem in narrowband Internet of Things. Components includes energy harvesting, NMA for spectrum efficiency, and relay assistance to improve data distribution. So for our problem formulation, the network's overlapping communication channels create interference. It makes the problem non-convex. So our proposed solution is to introduce a mathematical transformation to convert the problem into a convex form, enabling for optimal solution. So here is the step-by-step process of our transformation techniques. Step 1, we define the interference in NB-IoT networks. So we do this to quantify the interference experience by each device due to other devices sharing the frequency. Shown are our equation. Step 2, transmission power formula to allow the optimization of the model to handle power allocation dynamically by considering the interference. Step 3, we reformulate the constraint in order to control data rate and to ensure network stability and fairness. It ensures that the constraint that the data rate is within acceptable limits. Step 4, minimization of data requirement. To enforce a minimum service level, we need to balance the data rates for all devices, and at the same time, it must meet a minimum data rate to ensure fair access across the network. Step 5, we convert the optimization problem and transform a non-convex optimization problem into a convex form to simplify the solution process. We then introduce a Lagrangian function or LF to balance the constraint optimization problem. And this LF function will allow iterative adjustment as it incorporates constraint as a Lagrange multiplier. Step 7 is we apply a Karun-Kush-Tucker condition for optimality. So by applying KKT, each constraint's gradient is balanced against the objective gradient. It allows the adjustment for constraint on power fairness and data rates. Step 8, we reformulate the successive interference cancellation in order to improve signal quality across devices, specifically used for network edge devices. Step 9, gradient descent for power adjustment. So we adjust the power in each iteration to gradually optimize towards minimal interference. It is updated successively or iteratively based on the gradient with a specific learning rate. Step 10. We tend to converge through the iterative updates. So for the purpose of this enables convergence to the optimal power distribution. Through iteration on power, interference is minimized and network's efficiency is maximized. Step 11, we introduce a fairness constraint to maintain the stability and fairness among devices. For step 12, power allocation across multiple devices. So we have done this to manage the power constraint across the network for each devices to balance out against the total available power. Step 13, we provide constrained queue size and data rate as to prevent the under-provisioning of the network resources in order to meet the data minimum threshold for each devices. Step 14, the logarithmic transformation for convexity. We simplifies the algorithm or the equation by handling variables to ensure that the problems remain solvable in a convex way or a convex form. We use logarithmic transformation to achieve convexity throughout the optimization of the algorithm. And step 15, we have derived the final optimization objective, which provides a robust solution for NB-IoT network efficiency, for meeting energy, data rate, and spectrum fairness goals. By combining all this constraint and transformation to create an algorithm for an efficient network model. So for the results and discussion, so our simulation setup, we have the specific distance, the bandwidth allocation, the energy collected, the queue size as seen on the screen, and by assessing the reference, we compare it to a traditional frequency division multiple access or FDMA in order to highlight the advantages of the dynamic allocation of the proposed NMA-based solutions. So these are our results. So I will discuss this graph on the succeeding section. So for the baseline performance, according to the graphs, the simulations show improved resource utilization through dynamic bandwidth allocation. Also, the narrowband Internet of Things with energy harvesting relay setup supports multiple devices. It achieves a better resource use and efficiency compared to standard configuration. So we also have in terms of device count impact. So with increasing devices, the data rate and the spectral efficiency improve, though energy efficiency decreases due to the energy harvesting relay limitation. For the numeric comparison, we have a key improvement of 7.23%, 36.76%, and 31.93% in all the metrics. So in summary, our NMA outperforms the FDMA, particularly as device count rises. Also, in terms of transmission distance, performance degrades as distance between the EH relay and sync node increases due to reduced channel gain. Again, NMA remains superior, as you can see, on the quantitative improvement. As EA relay energy collection increases in terms of energy collection, so the fairness distribution improved logarithmically but not linearly. So NMA continues to outperform FDMA with 30.26, 19.22% gain in terms of spectral and energy efficiency despite diminishing returns at higher energy levels. Last, in terms of spectrum efficiency, NMA significantly boosts the efficiency by 36.70%. So this is particularly beneficial in crowded networks. In summary, our proposed model consistently show a higher performance metrics than the traditional setup with significant improvement in data rate fairness, spectrum efficiency, highlighting the effectiveness of the algorithm in high density IoT environments. For the conclusion, we successfully integrate NMA with EH relays to enhance data rate fairness, spectrum efficiency, and energy savings in NB-IoT networks. Our proposed model demonstrates superior performance over traditional methods, specifically in high-density, interference-prone environments. As for future research, we will focus on multi-relay configuration and advanced scheduling to further optimize network performance. Thank you very much for listening.